Assalamu alaikum, everyone. Today I've got a question for you. When you step on a weighing scale, or when you tell someone your height, have you ever think about what you're actually doing? It seems simple, right? But what you're performing is a fundamental act of science called measurement. So, what exactly is measurement? In the language of physics, it's the process of comparing an unknown quantity with a known, standard quantity. Think of it like this. You have a mystery bag of apples, and you want to know how heavy it is. You place it on a scale, which compares its mass to a standard, like a kilogram. The scale then tells you, hey, this bag is 3 times as heavy as that standard weight. And boom, you've just made a measurement. The result is 3 kilograms. Now, let's break the result down. Because every single physical measurement is made up of 2 crucial parts. First, we have the numerical magnitude. In our example, that's the number 3. It tells us the size, the how much part of the measurement. You'd probably give me a weird look if I just said 3, right? 3 what? 3 elephants, 3 seconds, 3 grains of sand. It's completely meaningless on its own. That brings us to the second essential part, the unit. In our case, the unit is kilogram. When I say 3 kilograms, suddenly everything becomes crystal clear. The magnitude 3 and the unit kilogram work together to give us a complete, understandable piece of information. It's like a first and last name. You need both to identify someone properly. Without a unit, a number in physics is just a lonely digit with no purpose. Imagine trying to bake a cake, and the recipe says add 5 sugar. 5 what? 5 spoonful. 5 cups. 5 tiny grains. You'd have no idea, and your cake would probably be a disaster. Units are super important. They turn numbers into useful data we can actually use. This brings us to a very important question. Why do we need a standardized system of units? Now, let's take a little trip back in time. For centuries, the world of measurement was, to put it mildly, a chaotic mess. Different parts of the world used their own local, and often quite strange, measurement systems. People used units like the foot, which was literally based on the length of a person's foot, or the hand span, the distance from the tip of the thumb to the tip of the little finger, or even a pace, the length of a single step. You see the issue. Everyone's foot and hand sizes are totally different, right? This inconsistency caused huge confusion in daily life and especially in science and international trade. Imagine trying to build a machine with parts made in different countries, each using a different definition of a foot. It would be a disaster. It was like trying to build a tower with bricks of all different shapes and sizes, a recipe for disaster. Scientists couldn't reliably replicate each other's experiments, and traders couldn't be sure they were getting a fair deal. An experiment conducted in France might yield results in one set of units, while a similar experiment in England would use completely different ones. This lack of standardization was a huge barrier to global progress. To solve this global mess, the world's scientific community decided to put an end to this confusion, and finally, a historic General Conference on Weights and Measures was held in Paris in the year 1960. It was a monumental event. Scientists around the globe teamed up to create a super simple measurement system for everyone. And from this conference, the International System of Units was born. In French, it's called Système International d'Units, which is why we abbreviate it as SI. This was a game changer. The SI system gives everyone a common way to measure things. So a measurement in Pakistan makes sense in Brazil or Japan. So, how does this SI system work? It's all based on 7 key quantities in physics, the essential building blocks that make up everything around us. And for each of these base quantities, the SI system assigns a single, specific unit. These are what we call the base units. Check out these awesome 7. First off, the basic unit for length is the meter. So we measure distance, height, and width in meters. Next, for mass, which is the amount of matter in an object, the base unit is the kilogram. For the measurement of time, the universal base unit is the second. For electric current, we use the ampere. For temperature, the base unit is the Kelvin. When we talk about the amount of a substance, especially in chemistry, we use mole. And finally, for luminous intensity, or the brightness of light, the base unit is the candelar. They're super precise and serve as the steady foundation for all scientific and technical measurements around the globe. Think of them like the building blocks of art with just a few colors. You can whip up endless new shades. In the same way, from these 7 base units, we can derive every other unit we could possibly need. Now that we've established our foundation with base units, let's build upon it. The next category of units in the SI system is called derived units. And just as the name suggests, these are units that are derived from or created by combining base units through multiplication or division. And let's take a simple and familiar example of speed. How do we measure speed? We measure it in distance traveled over a certain amount of time, right? Like kilometers per hour, or in SI terms, meters per second. See what we did there? We took the base unit for length, the meter, and divided it by the base unit for time, the second. Meters per second is therefore a derived unit. It's not one of the original 7, but is constructed from them. Let's look at another one, area. To find the area of a square, you multiply its length by its width. In SI units, you would multiply meters by meters. The result, square meters, or meters squared. How about something a bit more complex? Like force have derived units. The SI unit for force is the Newton. You might remember from your studies that force equals mass times acceleration. The base unit for mass is the kilogram. Acceleration is the change in speed over time, so its unit is meters per second squared. Force is measured in kilogram meters per second squared, but we just call it a Newton, named after Sir Isaac Newton. Almost every measurement in physics, like pressure, energy, density, and electric charge, relies on derived units. So, to wrap up today's lesson, we've learned that measurement is a fundamental act of comparison that needs both a number and a unit to be complete. The wild history of local units brought us to the unified international system of units, or SI, we use today. We checked out how basic units mix to create derived ones, letting us measure everything from car speed to rocket force. The SI system truly makes science a universal language, allowing for global collaboration and progress. I hope this has made concepts crystal clear for you. But our journey into Chapter 1 isn't over yet. In our very next video, we're going to tackle a super useful tool called prefixes. We use these to handle huge numbers, like the distance to the sun, or tiny ones, like an atom size, without tons of zeros. It's a simple trick that will make your calculations so much easier. Loved this video? Smash that like button, subscribe, and turn on notifications to ace your physics exams. Thanks for watching, and I'll see you in the next one.